Today I'll be presenting Lab 3 from Physics 2211. The purpose of this lab was to create a computational model to demonstrate gravity. In part 1, we used it to estimate the mass of a black hole based on the interaction between a star of known mass and the black hole. In part 2, we used it to find the initial velocity of the ship in a three-body gravitational system such that it doesn't crash into anything and is influenced by both a moon and planet's gravitational forces. The principles we used for this lab were the force of gravity, Newton's second law, the mass of the black hole, where the only force acting on the star is gravity. Therefore, the black hole's mass would be the formula below. The diagram for part 1, the system is the star, the surroundings are the black hole and everything else. The key assumptions are that only the force acting on the star is the force due to gravity, and the black hole is stationary. For our computational model, to the left, we have the initial conditions with the gravity constant and the mass of the star, and the time interval between imported data points, which would be 1 day. On the right, we have the actual computational model. Here you can see setting the initial velocity and vector. Here you can see where we calculated the momentum initial and momentum final, delta V, delta P, the change in momentum, F net, and through all these formulas, at the bottom we get the mass of the black hole by multiplying the magnitude of F net and the magnitude of the star position, squaring that, and then dividing by G times the star mass. The results we got from this lab was that the average mass of the black hole was 1.49 times 10 to the 34th kilograms. Setup for the second lab was a system with the spaceship. Surroundings were the planet, the moon, and everything else. The key assumption was that gravity is the only force acting on each of the objects and the planet is stationary. And in this lab, we wanted to figure out a velocity that the ship would have that would allow it to do an orbit around both the Earth and the moon without crashing into anything. The computational model we used for this one, to the left, you can see the initial values such as the gravitational constant, the mass of the planet, the moon, the ship, delta T. And then you can also see the moon speed and moon velocity, and the initial ship speed that we used was 2.45 times 10 to the 4th for both the X and Y direction to get the ship off of the moon. To the right, you can see the calculations we used to figure out the force of the planet on the moon, the force of the ship on the moon, the F net from the moon, and then we used another formula as well to find the force of planet on the ship and the force of the moon on the ship to get the F net of the ship. And then using these, we figured out the moon velocity and moon position, and then also found out the ship velocity and ship position based on the formulas we used above. The result was a diagram that looked kind of like this, where you can see the purple line is the ship orbiting around the planet, and its orbit being affected by the gravity from the moon as well. Sources of error for this lab was assuming the position of the planet does not change. In part 1, there may be better techniques to calculate the black hole's mass than averaging each individual mass. And in part 2, the time step in the beginning may be too long, and it would be more precise if shorter time steps were used. What does it mean? How is the net force and its parallel and perpendicular components different from the rate of change of momentum in its parallel and perpendicular components? Even though the two are equal, the way they are measured is different. To determine F net, you must know all the objects within the system, which is interacting. You also must know how it interacts with each of the objects. To determine change of momentum, you must know the mass of the system and be able to measure its motion. What if this imaginary system has a black hole and a star, a planet, and a moon? If you wanted to predict the motion of the entire system, what would you need to include in your computational model? Think about all the interactions in the system. Would there be any dominant interactions, or will they all contribute more or less equally? We need to consider all the forces acting on each part of the system and vice versa. There would be more dominant forces between the star, planet, and moon. Thank you. That is all for my presentation.